Welcome to the session 2.2. In this session, we'll be discussing about diffraction of light. So, in last session, we discussed 2.1 of the chapter optics, and in this section, we will start with refraction. So, I think I already told that what is refraction. Refraction is nothing but bending of light when it enters from one media to another medium. Okay, continuing with that paragraph. When a ray of light travels from one transparent medium into another obliquely in the sense it won't travel in a perpendicular manner, it will be traveling in a sidewards. That's called as obliquely. Then, the path of the light undergoes deviation. So, this is called as refraction. Okay, this is quite clear. Then, this deviation of ray of light is called as refraction. So this is the definition of refraction. Then refraction takes place due to the difference in the velocity of light in different media. So if you take something for an example, if light is going to enter from air into water, so in air the speed of light is 3 into 10 power 8 meter per second. But when it enters into the water region, the speed will be decreased, something like 2 into 10 power 8 meter per second. So that difference will create refraction. The speed of light is going to decrease in water, so there is some phenomenal change, and hence this leads to refraction phenomena. Medium here is referred to transparent medium through which light can enter or travel. Then the velocity of light is more in a rarer medium and less in a denser medium. So why actually they are saying this is uh, rarer? If there is no hindrance in your path, while you are walking in a road, if there are less number of people crossing you, then you will walk faster. But take the vice versa case. If there are many people walking in the road, you will take longer time to cross the same distance. So that's what here light is also doing. In rarer medium, light will travel faster. For example, air or vacuum. And the opposite thing is that in denser medium, light will take more time. So it travels in less velocity. And for this, the example is water. Then, refraction of light obeys two laws of refraction. So in last class, in ninth standard, you might have studied there are two laws of reflection, and here you will be studying two laws of refraction. Okay, paragraph clear. Coming to first law of refraction, the incident ray, the refracted ray of light, and the normal to the refracting surface all lie in the same plane. This is very simple. See, in first law of reflection, I am going to talk about reflection. We will be taking a plane mirror, right? Take a plane mirror, and this upper side is the reflecting surface, and this line is normal. So normal is always perpendicular to the plane of reflecting or refracting surface, and this is going to be the incident ray, and this will be the reflected ray. And if you see this incident ray, this normal, and this reflected ray, all three is going to lie in the same plane, that is plane of the reflecting surface, and this is called as first law of reflection. So what they are going to say here is very simple. Take this as the interface between two media, that is air and water. So normally if you take a water tub, the upper portion will be air and the water containing portion is water. I'm sorry for that. And this is the interface. So we are going to draw normal. This is normal, which is always perpendicular to the interface or the reflecting surface, and this is incident ray. This is going to incident, and as usual this might travel in this path. but due to refraction this will travel in this path. This is refracted ray, this is what is it, this is incident ray, and this is normal. So if you take note of this, all these three, this one, this normal, and this refracted ray is going to lie in a same plane, that is interface between two media. That's what they are saying in the first law of refraction. And then second law of refraction needs some extra knowledge, and they are going to give it in this part. So we will be doing this part first, and then we are going to do this thing. This formula is very important, and you will be using it till 12th standard. So this symbol, you might be knowing this symbol. This is called as mu actually, and this symbol is used here, which is denoting refractive index. So what is refractive index actually? We need to have some idea, or we need to have some knowledge about what is refractive index before knowing this law. So here they are giving that refractive index gives us an idea of how fast or how slow light travels in a medium. So actually they are giving two things: how fast, how slow. So what it is going to denote? We are going to see that the ratio of speed of light in vacuum, I will be writing here, the ratio of speed of light in vacuum is c. It is denoted by c, and since they are writing a ratio, so I will be dividing, and then to the speed of light in a medium. So speed of light in a medium, this is m probably. This is called as refractive index, which is equal to mu m. So here m denotes refractive index of medium. C is speed of light in vacuum. So what is the speed of light in vacuum is 3 into 10 power 8 meter per second. So anyway, if you're going to go or run in a road where there is no person, you will be having your maximum velocity. But if there are some person, then you will lack some velocity, you will be below that maximum velocity. So that's what light is going to do here. In vacuum, it is going to travel the fastest, that is with the speed of 3 into 10 power 8. But if you take in water, it is going to travel in 2 into 10 power 8 meter per second velocity. So that means 3 into 10 power 8, I just write e, 10 power 8 is e here, and 2 into 10 power 8. So we are going to find what is the refractive index of water, W. E gets cancelled out, that is 10 power 8 and 10 power 8 will be cancelled out, and 3 by 2 will be cancelled out, and finally we will be having 1.5 refractive index. So by using this formula we can say refractive index of water is 1.5. So what it is denoting actually, we need to learn this. Okay, for more clearance we can find refractive index of vacuum first of all. So what the formula says is that ratio of speed of light in vacuum, so 3 into 10 power 8, I am denoting it as E. Actually it's not E, but assign it is E. Then speed of light in a medium. So here we are going to take medium as vacuum. So what is the speed of light in vacuum? Same, 3 into 10 power 8, 3 into E. So E gets cancelled out, and 3 gets cancelled out. So finally refractive index of vacuum is 1. And in before case we took refractive index of water as 1.5. So which one is bigger? Everyone knows that, right? 1.5 is always bigger than 1. So what does this mean is that if refractive index increases, then speed of light decreases in that medium. So if you take an example for diamond, which everyone know, diamond, which will shine better. So refractive index of diamond is nearly, I don't know how much, maybe 4 I guess. Refractive index of diamond is 4. So if you pass the light through the diamond, it will take a longer time to cross it. Why? Because refractive index is more, so diamond is going to create more hindrance to the passage of light. So light will be having lesser velocity when compared with the vacuum. So for simple I can say that refractive index is just a quantity which says how slow light can travel. If refractive index is more, then light travels slower. If refractive index is less, then light travels faster. Anyway, we need to know one thing. Refractive index cannot be lesser than 0. Lesser than 1, because vacuum is the empty space we know till now. So in vacuum, the refractive index of light is 1. So anyway, anywhere, we won't be finding refractive index lesser than 1. It will be always greater than 1. Okay, refractive index over, right? 10 minutes over, fine. We'll be going to the law first of all. The ratio of the sine of the angle. Sine of angle is very simple. Sine of angle. I'll be drawing a diagram. You will understand it later. Sine of the angle of incidence, say I, and sine of the angle of refraction. They took ratio, so divided by sine r is equal to the ratio of refractive indices of the two media. So mu2 is the lateral media and mu1 is the first media. So just for the diagram sake, I'll be drawing, this is the interface actually, and this is mu2. Mu2 is second medium and mu1 is first medium. For convenience, we'll be taking it as air and water. That's enough. This is just water, just for drawing purpose. Okay, so this is normal line. Anytime we will be drawing this perpendicular actually, and then if light is going to enter in this direction, it must go in this direction, right? But due to refraction, this will bend in this direction. So this is incident angle. We need to draw arrow. Okay, this is incident angle and this is refracted angle. For clearance sake, I will be drawing it once again. Interface, normal, incident line, incident ray. This is the path the light must go if there is no interface, but actually there is interface. mu2 is there and mu1 is here. This is angle of refraction and this is angle of incident. So here we consider mu1 is lesser than mu2. So what does this mean? In mu1 light can travel faster, but in mu2 light travels slower. So that's why it is going to bend towards normal. This is just the representation. So for the law, we need to take sine of I. So if this angle is 30 degree, then you need to take sine 30. So what is sine 30 is 1 by 2. You need to take 1 by 2. First of all, we need to write 1 by 2 instead of sine I, then divided by sine r. So what is r? R might be 15 degree, maybe, 15 degree. We don't know the value of sine 15 degree, so we can write sine 15 as well. So what will be that is 1 by 2 divided by sine 15. Sine 15 is equal to mu2 by mu1. So why they took the inverse actually is very simple. It's also quite interesting, See, if you take sine r to this side and mu1 to this side, you will be getting mu1 sine I, which is equal to mu2 sine r. Sine r is refracting angle and I is incident angle. So mu1 is upper media and mu2 is refractive index of second media. So this can be easily memorized. mu1 sine I and mu2 sine r. If you think conceptually, you will be getting what is going on. So that's all the law. Okay, that's all the law. And you need to memorize the law. You need to memorize each and every law. Laws are very important for scoring marks in physics, and this formula is going to help you in later portions. Then we completed this paragraph. The speed of light in a medium is low if the refractive index of the medium is high, and vice versa. This thing I already told. I just told now. See, speed of light in a medium is low if the refractive index of medium is high. In diamond, refractive index is 4. So the speed of light in diamond is very slow. See, there comes the rhyming. Uh, what is that? I'll be repeating it. The refractive index of diamond is 4, so the speed of light is slow. Rhyming, super na? uh, just for fun. And then vice versa is just the inverse. The speed of light, I'll be saying it, the speed of light in a medium is high if the refractive index of the medium is low. That's what they wrote as vice versa. Then when light travels from a denser medium into a rarer medium, the refracted ray is bent away from the normal, drawn to the interface. And the last point, we'll be seeing it. Wait. When light travels from a rarer medium into a denser medium, the refracted ray is bent towards the normal, drawn to the interface. So actually, okay, fine. So what they said is very simple. Just one diagram. Same diagram. Interface. Take this as rarer medium. Rarer medium is air. Just for example, I am taking air, and this is denser medium. That is water, and this is normal. This is incident ray, and this incident ray must go in this direction if there is no interface, but due to interface it is going to be refracted towards normal. Why it is refracting towards normal? The reason is, in denser medium speed of light is going to be reduced, so that's the cause of refraction, and that's why it is also going to be leaning towards normal. So if light is going to enter from rarer to denser, it is going to lean towards normal. So you must actually remember this. There is no other way. You can use mnemonics to remember these things. And if go in this direction, actually, okay, fine. If light is going to go from denser medium, like this, denser medium to rarer medium, it is going to go in this direction if there is no interface, but hence there is interface, it is going to bend away from normal, because light speed is going to increase if it enters rarer medium, so that's why it's going to bend away from normal. So this one diagram is enough to remember you everything. Just take air and water, use the concepts, and you will be getting what is happening in the last 2 points. And that's the session today. In next section we will be discussing about refraction of composite light, dispersion of light, these things and all, very easy things, but we will be doing it later on. And what's the time now? 18 minutes 23 seconds, 24, 25. Okay, fine. And if you like my videos, subscribe it. I'm sorry, if you like my videos, like it, and if you wanna share it, and then wanna subscribe it, click the subscribe button. Okay, fine. It's struggling a bit. I will handle it. Thank you. Bye bye.